Welcome to my invited talk on the polar vortex. I am Kalevi Mursula, Professor of Space Physics at the University of Oulu, Finland. Oulu is located at the 65th northern latitude, often below the polar vortex boundary. Actually, when I was making this video in early January 2021, the polar vortex was recently split and shifted southward so that the northern Finland was at the center of the polar vortex, not at its boundary. Anyways, polar vortex is a circular system of strong westerly winds in the high latitude stratosphere, which develops each winter around the winter pole due to the temperature difference between the warm tropics and the cold winter pole. The effects of the polar vortex are seen on the ground as the climate pattern called the North Atlantic Oscillation or the Northern Annular Mode. The strong polar vortex favors the positive now-NAM phase pattern with warmer Eurasia and colder Greenland and North Canada. A weak polar vortex favors the negative now-NAM with opposite temperature and pressure changes. Now depicts considerable temporal variation from winter to winter. This is often called the decadal variation, although it does not have a notably clear decadal periodicity, nor an obvious relation, for example, with the sunspots. In order to study the possible relation of now with the solar cycle, we divided the solar cycles 11 to 23 into 4 phases: the ascending, maximum, declining, and minimum phase, each denoted by its own color in the 2 lower panels of this figure. We then assigned each winter to one of these 4 phases. We collected the winter temperature data separately in the winters of the 3 different cycle phases for these cycles. The only significant signals that are found in any of the 4 phases are in the declining phase, where the pattern forms the spatial distribution, which is very closely similar as the positive now pattern. Positive and negative now index values can appear in all solar cycle phase winters. However, winter now is statistically different from the long-term mean only in the declining phase. Now index is positive in 12 out of 13 declining phase winters. So there is a decadal solar cycle related variation in the now index and pattern, but it is not directly related to sunspots, but rather so that the positive phase of the now is favored in the declining phase of the solar cycle, out of phase with sunspots. This is a new important fact, which any major driver of now must naturally explain. Several climate drivers have been suggested to affect the polar vortex, for example, sunspot activity, which is a proxy for solar total and spectral irradiance, the ENSO, volcanic aerosols, quasi-biennial oscillation or equatorial winds, so-called QBO, and planetary waves, etc. However, these drivers do not have, or at least are not known to have, a natural preference for the declining phase of the solar cycle. Therefore, they do not naturally explain the relation of now with the declining phase. There is one more suggested now driver which does have a natural relation to the declining phase of the sunspot cycle, and that is the magnetospheric energetic particles, which is often equated as the so-called geomagnetic activity. The EPP particles, these energetic particles, are typically from 1 keV to 1 MeV electrons, mainly electrons. EPP particles are mainly produced by high-speed solar wind stream interaction with the magnetosphere. Both high-speed streams and the EPP particles naturally maximize in the declining phase because of the systematic evolution of solar magnetic fields and solar coronary poles, which produce the high-speed streams. Correlating winter ground temperature with EPP produces a global pattern which greatly resembles the now-NAM pattern. This is natural since the decadal variation in EPP and the now index is similar with maxima in the declining phase. Note also that the range of variation at the site of maximum correlation is very large, several degrees, about 5 degrees. We have done also a multilinear regression study of the response of the polar vortex, zonally average zonal wind at different latitudes and altitudes, to 5 drivers separately in 4 winter months. Responses to each driver, these are the energetic particles, here represented by the geomagnetic activity AP index, the sunspots, the ENSO, volcanic aerosols, which is represented by the aerosol optical depth, AOD, and the quasi-biennial oscillation, QBO. They are shown in rows for each month, which are depicted as columns. Now the EPP or AP causes the strongest and most systematic response, enhancing the polar vortex in all months. Sunspots cause only a weak negative response to polar vortex. Thus, the so-called top-down mechanism of solar irradiance does not seem to enhance the polar vortex, contrary to some earlier studies. Other driver responses are as found in most earlier studies. Correlating the winter ground temperatures with EPP separately for winters of easterly and westerly QBO at 30 hectopascal height phases, we found a strong now pattern only for the easterly QBO phase. The pattern for the westerly QBO phase was insignificant. Note also that there is a Holton-Tan relation, according to which the QPO easterly phase weakens the polar vortex by directing planetary waves to higher latitudes. Does this have any relation to the EPP effect? We'll study that shortly. The most dramatic event in the polar vortex stratosphere is the so-called sudden stratospheric warming, SSW, that breaks the polar vortex in the middle of the winter in some winters, roughly every second winter in the northern hemisphere. Note that this process is ongoing above me right now, as I'm making this video. It will soon bring very cold weather for the next couple of weeks, just ahead of me now. We'll see. Anyways, the Holton-Tan relation is verified by the fact that many more warmings occur during the QPO easterly phase. There is also a weaker preference of low EPP producing more warmings than the high EPP. ENSO or sunspots have no effect on sudden stratospheric warming occurrence. Separating the winters by 2 drivers, QPO and either EPP, ENSO, or sunspots, we find that almost all winters with QPO easterly and low EPP lead to the warming. So the low EPP seems to further enhance the Holton-Tan effect. On the other hand, high EPP tends to increase the relative number of no warming winters for QPO easterly, thus reducing the Holton-10 effect. There is no effect of EPP on the warming occurrence in QPO westerly in agreement with the above results for the polar vortex in more general. Selecting only those months that precede southern stratospheric warmings, we find that the EPP effect, the polar vortex, is strong in all winter months. No SSW winters. In no warming winters, it is insignificant. Strong EPP enhancement is associated with anomalous warming in the upper stratosphere, cooling in the lower stratosphere, anomalous divergence of planetary waves in the middle stratosphere, and a reduction of downwelling, that is adiabatic adiabatic cooling of the lower stratosphere. The pre-warming times here from 5 to 15 days before the warming are characterized by weaker than average zonal wind, which is due to the enhanced planetary wave activity, obviously, strong planetary wave convergence, which drives enhanced downwelling and is seen as enhanced adiabatic heating and increased polar stratospheric temperature. These conditions allow the EPP to enhance the polar vortex according to the scheme to be suggested next. The scheme for the possible mechanism for the amplification of the EPP response by the planetary waves includes a feedback loop consisting of the 4 effects that are listed in the slide. Unfortunately, I will have no time to go into detail in this, but this loop works most efficiently with a sufficient level of planetary wave activity, which eventually also causes a subsequent warming. Since planetary waves are stronger and the warming is more common in the QPO easterly phase, the suggested mechanism explains also why the QPO modulates the EPP response to the polar vortex. Okay, finally the conclusions. The now index and now pattern have a decadal variation, which has been actually quite hidden so far, which has a positive phase in the declining phase of the sunspot cycle. This imposes a strict constraint on any major climate driver aiming to affect the polar vortex. Solar wind accelerated magnetospheric energetic particles naturally peak in the declining phase. They are the main solar-related driver of the polar vortex and comparable to any terrestrial driver. Effects of solar irradiance, on the other hand, to the polar vortex are negative and rather weak. The EPP effect is strong in all winter months in the QPO easterly phase. Sudden stratospheric warmings are enhanced beyond the Holton-10 effect if the EPP is low and they are reduced if it is high. EPP effect occurs mainly in the SSW, so warming winters, some weeks before the onset of the warming. This can be explained by a feedback loop mechanism produced by the wave mean flow interaction. This mechanism works more efficiently when sufficient planetary wave activity is present. In this mechanism, the QPO modulation of the EEP response to the polar vortex is due to the stronger planetary wave activity of the QPO easterly phase. So, some references here. And then I thank you for your interest and hope to hear from you. My contact is in the email. Thank you very much.